Welcome once again to this course on digital communication. We discussed about different types of signals in the first session. The second session, the effect of noise. Here, let us discuss about the sampling theorem. Before we talk about sampling basically is, collecting a few samples of the data and estimate the entire process. So a very common familiar example is when you are cooking a particular dish and you want to make sure that it is cooked properly. You don't take all the grains and test. You take a few sample of grains, make sure that it is cooked properly. Thereby you conclude that the entire dish is cooked. Similarly, when you take large amount of data, from the data, and if you want to analyze, you cannot big data. Nowadays the problem is the data is big, voluminous data. So to analyze, what you do is you collect different samples and make some analysis. Whatever parameters you want to measure, you can measure and integrate it for the entire thing. So suppose you are conducting an experiment using a microcontroller. You want to monitor the temperature of a furnace, and you set a temperature, let us say some 1000 degrees centigrade, and the temperature has to be maintained for a particular experiment. So you supply heat by means of an oven, and for every 10 seconds or 60 seconds, whatever be, depends on the experiment. For regular intervals of time, you want to monitor the temperature of the furnace. To reach that temperature, it takes a very long time. So humanly, it is quite difficult. So we make use of microcontrollers or any other processors connected to that system, and then see that the temperature is recorded, and let us say that the temperature has to be maintained. If it falls, some alarm signal has to be given. This is one example. Another can be medical applications. You have all these ventilators and other things which monitors the heartbeat, pulse rate, and so on. Nowadays in this COVID situation, all these are automated. So what they will do, they connect their instrument and then it keeps on checking, collecting different samples of a patient, and this is known as remote monitoring of the patient also. So when they take at different intervals of time, they monitor their heartbeat and so on, and when it is normal, it will be monitoring. If any vital signs are changed, vital parts are all parameters are changing, then the information has to be alerted to the consulting doctor. So what is happening? You are actually taking different intervals of time throughout of a person undergoing treatment on a ventilator, and if there is any change in the vital signs, it has to be intimated to the doctor. So what is this happening here? Monitoring is continuous. So the process of measuring is instantaneous. The signal is continuous time signal. But your measurement is discrete in nature. How do you say it is discrete in nature? You are monitoring the patient's condition every hourly or every half an hourly, depending on the seriousness of the patient, and you are reporting. So that is discrete in nature. So what is the definition? It specifies the minimum. Now, this is the definition. Then how frequently are you taking is the frequency. Frequency refers to the rate at which this signal is being sampled. Why are you doing this? Because you are reconstructing the signal by taking the samples. So the rate at which it is recovered is referred to as the sampling theorem. So sample is nothing but a piece of data taken from the whole data, which is continuous in time domain. Now what is it actually you are doing? You are taking a signal and you are reconstructing. is it actually you are doing? Analog to digital, digital to analog. Say, why is this needed? Let me give you another example. So suppose you are talking on a telephone and you are connecting to computers. Voice messages you are giving, and your voice messages, your Google Assistants, what are they all doing? They're communicating between two computers over the internet. Now, voice is converted into text. The text is entered into the computer, transferred over the net to the other end to another computer. So what's happening here in the first stage? Your voice is analog in nature, has to be converted into text, and that text has to be entered onto the system. So analog to digital conversion is taking place. The digitized data is sent over to another computer. At the other end, again you are listening to the voice only, you are not listening to the text. When you type your voice message, it's your voice that is heard at the other end, traveled over the net. Again, it is reaching the next system in a digitized form that has to be reconstructed back to analog so that you are able to hear the voice whoever is talking to you. Earlier it was telephone messages, now it's our electronic messages. Google Assistants, Alexas are coming. So this is a voice. You also have voice over internet protocol, VoIP it is called, or interactive voice system. Whenever you are booking any complaint anywhere, what it is actually doing, it is a voice actualization system, voice recognition system. So what does this voice recognition system do? When you want some help, if you want to talk to a receptionist or an executive, what you have to do. If you are complaining, say suppose a telephone you are complaining, if it is a faulty telephone, press 1. If it is completely dead, 2. So these are all voice actuated systems. All these are conversions that are taking place. In simple means, we call this as a modem. Modem means what? Modulation at one end. Modulation means what? Why do you need a modulation? When you want to send a signal from one place to the other, if the signal is weak, the signal what you are sending is a function of time and frequency, and the low signals will have less energy because energy is h nu. H nu, H is Planck's constant, nu the frequency. More the frequency, more energy. So say suppose, let me take an example of, you want to attend to a musical concert somewhere. If it is a walkable distance, you will walk, go and come back. Or if you are going to a college and if you are staying nearby, you will walk and come back. But if you are a little far, you cannot walk, then you need a vehicle. You need to be transported in a vehicle to the college. So you as a person is considered as a signal or an information, and if this information has to be transmitted over longer distances, you need a vehicle. That vehicle is called carrier. You are mixed with carrier and then you are transmitted. So this process is known as modulation. Then the vehicle will not be going into the concert or into the college, it will drop you there. It is you who have to go there. So recovery of the signal, that is demodulation. That analog to digital is it's converted. At the other end, at the receiver, again digital back to analog. So this is how the discretization is taking place. So if you take this as the original signal, it's continuous time. It's continuously varying in time. You see so many ups and downs. Okay. You can also take an example of a music. When you are talking, your speech, that's all analog. We will not be talking continuously at the same tone and same pitch. When you look at your graphic analysis on your systems or wherever you are recording, when you see, now it's all digital recording. So when you take your mobile phone, start talking with the voice recorder, you all must be knowing this. When you talk, you can see that graphs, it's vertical histograms. You can see that it's going up and down at different levels. That shows how your voice is varying over time. So that's analog in nature. Now the same thing, if you want to represent it and see how your voice is changing over time, you sample at different intervals of time. This is sample. So it's going high, so this is high. 0, so almost close to 0. Negative peak going to negative peak. Positive peak going up. This is the highest, and this is the lowest. So this actually is what is indicating. So when you are doing this signal is continuously changing. So suppose you are monitoring the temperature of a furnace, okay, at different intervals. This is how you will be doing it. Excuse me. This is how it is sampled. It is a function of time. Now, how many samples will you take and how much time you take is what is determined by, known as a sample rate. So, at what intervals? That interval refers to the gap. The gap is nothing but frequency or a time period. One is reciprocal of the other. This is the sampling time. This is sampling frequency. The rate denotes the number of samples taken per second or for a set of values. And the sampling rate should be such that there should not be any loss of information and there should not be any overlapping. And this rate is called as Nyquist rate. So the overlapping means the signal should end here, another signal should start here. If there is small gap given here, the gap should be allowed. Otherwise what happens? This will overlap with the other. You get disturbed signal. It's known as an overlapping signal. So don't take the intervals too very close. Take at regular intervals of time. The frequency should be in such a way that there is no overlap of information and then no loss of information. So fundamental criteria for any communication system is no, there should not be any apparent loss of information. So this is about sampling theory. Let us see. To further extend this sampling theory, let us describe and define some data levels, signal levels, over which the communication can be sent. So, we have seen how it is sampled, and now let us see the rate at which the data is sent. That is, how fast are you sending the data? And it is measured in bits per second. Number of bits per second that determines the speed of the signal. When you are sending the signal over a system, it requires a medium, and that medium is known as channel. Channel is nothing but bandwidth. So this data rate depends on bandwidth that is available and strength of the signal. The higher the strength, longer the distance, and quality of the channel. So based on this, Nyquist theorem says for communication which has to be sent without any noise, we've seen the presence of noise and how it affects the efficiency. So we don't want noise to be there, we want noiseless communication. Then the capacity of the channel is given by 2b log 2 power n to the base 2, where b is the bandwidth in hertz. There, the digital signal can be represented by more than 2 levels. 2 levels represents 2 bits per each level. So take this example, train of pulses. All digital signals are represented by square wave train of pulses. So here, how many bits you are sending? You are sending 8 bits. How much time? 1 second. You are sending 8 bits per second. And there are 2 levels here. What are the 2 levels? This is 0 level, this is 1 level. 1, 0, 1, 1, 0, 0, 0, 1. 8 bits per second is its bandwidth. The same signal, now if you see, it is sent at 4 different levels. Suppose you attribute, this is only an example. If this level 1 represents 0, level 2 represents 5 volts, this is 0 here. If at the same signal is represented like this, it's plus 5 plus 10 here, and this is minus 5 and minus 10 here. So how do you send this? 2 bits at a time you are sending here at a time. 1, 2, 3, 4, 5, 6, 7, 8, 8 into 2, 16 bits per second. So you are sending more number of bits here per second. The information is more. Okay. So, and when the information is more in a short span of time, the speed also is increased, frequency is increased, and you can send large amount of data in short interval of time, and the energy content also will be accordingly high. So the quality also matters here. Let me take the example here. A digital signal which has 8 levels, then how many bits are required? So 8 log 8 to the base 2 is log 2 to the power 3, 3 log 2 to the base 2. This is 1, so it is 3. So this signal in this example requires 3 bits to be able to represent it. Another example is, so let me take the example of high definition TV. Nowadays people are talking only about high definition. High definition is clear picture, sharp focus, and you should be able to distinguish and see the image clearly on the TV. That the kind of TVs are called high definition TVs. Let me take an example of a digital signal. This is being broadcast on a HD TV. Normally the screen is, this is called the aspect ratio. This is width and this is length. 16 by 9. And this 16, the entire TV screen is divided into 1920 by 1080 pixels per screen. What is a pixel? It's an intersection of row and column. Okay, so there are 1920 pixels along width and 1080 along the height. And then screen is renewed 30 times per second. Means what? In a second, one frame is 1920 by 180, 1080. Like the 30 times the refresh rate. So many images are being sent in second. And these images, when they are sent in seconds, so many times, it gives a moving picture effect. So that's a video that you are seeing. And each color pixel consists of 24 bits. So now let us see how do you calculate this. What is he asking you? The bit rate. So 1920 into 1080 pixels, and 30 times the same is repeated. The entire screen is repeated 30 times 30, and each color pixel requires 24 bits, so multiplied by 24. It requires so many gigabits per second. So what does a TV station do? It reduces to 20 to 40 through compression. Such a big file. See, when you are sending big files in your mails and all, they'll ask you to compress and send. Okay? So this is compressed to 40 Mbps. Different compression techniques are available. So this is how it is done. One more example, for a noiseless channel of 265 kilobits per second with a bandwidth of 20 kilohertz, how many signal levels do we need? So once again we use Nyquist formula. This 265 is the capacity, is equal to 2 into 20,000 bandwidth log L to the base 2. L is the level. And then you divide by this. L log L to the base 2 is this. So L will be 2 to the power this. So which is equal to 98.7 levels. Generally the levels are expressed for a signal in powers of 2. Since it cannot be expressed, either you increase the bit rate, or number of levels have to be reduced. So if you keep it closer to 128, the bit rate is 280 kilobits per second. 64 levels, it will be 240 kilobits per second. So accordingly it will be done. So this is how you will explain the sampling theorem, the signal level.